Good afternoon, everyone on Zoom. If you can hear me well, it'd be appreciated if you give me a thumbs up. Thank you, Andrew. Okay. I think it can be seen well. All right, so we can go ahead and begin. Sorry here for the delay. Um, let's, as usual, good afternoon. Let's speak a little bit about course logistics before we dive into our lecture. So, where we are currently, grading should be done. So you should have received all your grades for the programming assignment. And that was done by the TA, I think, this weekend. So if there's any issue with your grade, reach out to the TA that left a remark, and then they can definitely help you out. So where we are currently, we're in week 9. So this is the last lecture for chapter 3, the transport layer. And then on Wednesday we won't have a lecture, and then next Monday will be our midterm. So the idea for the midterm is that, as I mentioned over and over on every lecture that we had previously, is that the midterm is going to be similar to the homework. It's going to basically cover ideas that we covered from the beginning of semester till what we covered now in the transport layer. And it's going to be similar style to the homework, where you might have to do some sort of hands-on and write a report and take pictures, and then it'll roughly be maybe around the same amount of questions for the homework, maybe 5, 6, but has several parts as usual. So we'll open up on Monday, like around, for example, 6 a.m., and it'll be due the same day at 11:59. So I'll also make an announcement for those that are not attending in person or on Zoom, to just have that announcement as official, and I'll include all the details that we mentioned over in class, and all the official details. Okay, so just keep in mind, no lecture on Wednesday. This will be for you to review the material that we have been discussing so far, and then I'll see you on the next Wednesday, which is going to be the one on the 22nd. Yes. Okay, so where we are last week, we discussed congestion control as a protocol itself, or some ideas or mechanisms, but we haven't dived into the TCP congestion control, and we want to see what it uses. So just a touch up on the last lecture to get you guys in the same page for us to start on the next lecture. I just want to talk about two main things. I mean, we talked about the different scenarios where we need congestion control, and how it's important in TCP. And we know with UDP, it does not have congestion control whatsoever. So we want to know, how does TCP utilize congestion control? And also, we talked about flow control for TCP, and we know how to manage with that. So we left off with two approaches for congestion control. And we said there is those two approaches. There's going to be a lot of mechanisms or algorithms that will fall under these approaches, and that we will see in today's lecture. But basically, end-to-end congestion control is that the network itself, whether it's the transmission links or the routers, the switches, they don't have a say in the congestion control idea. End-to-end basically is, it's going to communicate from the receiver and sender. So based, what are the indicators for us to know there's congestion? We said there is an indicated timeout of the packet that is being sent. After that time runs out, this is one indicator for us that there's some sort of congestion or lost. Another indicator is that if we receive a duplicate of 3 acknowledgements, so we send packet 1 and 2, and received 3 acknowledgements for packet 1 because it was either congested or dropped or lost. So that is our 2 ways to make sure that, hey, when we see these 2 things, we have congestion and we need to deal with it. When the window size we talked about, basically it's a window size that has various phases, and I will cover it again to get you back to it as a summary. But it's basically every time we receive an acknowledgement, we do an increment of the next byte or the next packets. So, and that is the visual of the congestion control for end-to-end approach. So we basically deal with the client and server and the acknowledgement that is getting back from both either side of them. Here we give a human analogy to support the end-to-end. And then we have the network assisted control, congestion control, where the routers themselves give explicit feedback to the sender or receiver that lets the sender know, hey, there's congestion that's happening here. We need to find a way to slow it down where this doesn't happen over and over. And basically you can see here the routers that have buffers, they have explicit congestion info that is being sent to the sender and receiver. It tells the receiver, hey, there's congestion when you're getting this. That lets know the sender back. And we will gonna see the protocols that fall under this specific category. And then that's it. We left here, and this is where we're gonna follow up TCP congestion control. Is there any questions before we begin? Course related on the last lecture? Okay. Okay, let me just put this up. Okay, so as usual, the lecture is recorded and can be accessed on the Zoom navigation of WebCourse, and some of the slides are amplified or used from the book, and that's the direct link to it. So where we are currently, we're stick to our roadmap for every chapter. And so far we discussed the transport layer up till the congestion control for TCP. And at the end of the lecture, I'll do a brief recap of everything we covered so far. So first, to give you understanding of what's going on, we said in the last lecture, there's 2 approaches. Right now, we're going to start with the first approach, end-to-end approach. So there's really there's no network assistance that is being involved from both sides. So the first, you can say algorithm, or you can say mechanisms that falls under the end-to-end approach is called AIMD. And it's basically short for additive increase and multiplicative decrease. So it's the core behavior of TCP congestion control, where we have the sender gradually increases its sending rate as long as there is no packet loss. And they want to send or probe on the bandwidth of how much the network can handle. So that is the idea. Once we receive that limit or that mark of the congestion, then we need to start decreasing. So here's the idea on a given graph. We have the graph here, and the graph shows the time on the x-axis and the sending rate on the y-axis. So we start sending a sequence of bytes, and the sender increases its rate linearly. So that is the additive part of AIMD, right? When a packet loss happens, that is the second part, which is multiplicative decrease. So we have the additive increase, where we increase linearly by 1 on the given sequence or segment. And then once we reach the congestion point is where we do the multiplicative decrease. So we cut the sending rate in half. And that's basically what we are doing. So as you can see here, the repeated pattern that you can see here is kind of like a sawtooth shape, and it's a repeated pattern that shows kind of a combination of growth and sudden drops. So the AMD, the technique itself is a probing. When we say the word probing, mean we are trying to find the maximum throughput or the maximum sending rate without having that congestion issue. So that is what it's doing. We start with a sequence, we linearly increase, and then once we reach that congestion phase, we drop and cut the sending rate in half. So overall, this mechanisms is what keeps the network stable, efficient, and fair across multiple users. We're going to talk about TCP fairness as well over multiple users, but that is to come. So a closer look into the multiplicative decrease, and we said this is part of the algorithm. So we know that when a TCP detects packet loss, and we know to detect packet loss, we either have we get a notification of triple duplicate acknowledgements or the time runs out. So when TCP detects packet loss through triple acknowledgements, that's called TCP arena. That is basically an indicator for 3 duplicates. And TCP Reno and TCP Tahoe fall under the TCP AMID algorithm. For TCP and Reno and Tahoe, they fall under the multiplicative decrease part. So once we have triple acknowledgements being sent as acknowledgement, we use TCP Reno, and that cuts the congestion window size in half. But if we detect a timeout, meaning there's no acknowledgements that came at all, we use the TCP Tahoe, which the sender goes all the way back and resets it to 1 MSS, which is the maximum segment size that is being sent. Now you might ask yourself, why do we use this specific algorithm? First thing that you have to keep in mind is there's going to be a development of algorithms that we'll study throughout this lecture. But so far, as a beginner phase, AMD works as a distributed and a synchronous algorithm, and that's shown us that it adjusts its own rate independently based on the feedback. It is shown that it can optimize network-wide flow states, allowing bandwidth that gets shared with multiple active connections, and it also provides stability, keeping the network efficient without wild oscillations like back and forth or congestion collapse. So I try to include an analogy for everything that we discuss, so it kind of makes sense to you. So here, the analogy that we have for the algorithm that we discussed first, the AIM, that has the 2 phases that we said. The phases are multiplicative and additive. So we increase and decrease, basically. So here it says, imagine you're driving on the highway and trying to go as fast as you can without causing an accident. So the additive increase is you drive casually. Every few seconds, if the road seems clear, there's no traffic, and the traffic is flowing, you slowly press the gas pedal to increase your speed a little bit at a time. So that is like the TCP gradually increasing its congestion window. That is the additive increase. So we add a small amount of data each round when there is no congestion. The multiplicative decrease is when you suddenly notice the traffic is getting dense or there's almost bumps into the car ahead. This is a sign of congestion. So you say, hey, you slam the brakes and you cut your speed down by half to avoid a crash. And this works as the TCP multiplicative decreases its window size. And we said we have 2 ways of cutting, and that is back in the old slide. We have cut in half when we receive triple duplicates acknowledgement, and that is TCP Reno. And then we have 1 MSS. We cut down to 1 MSS when we use TCP Tau. So that is that. You can consider, and I think the book, or generally, they consider these as 4 different algorithms that are there, but it falls under the same umbrella. Okay, so the window size is something that is gonna be there, and it's gonna help us and assist us with congestion. And we know that the idea so far may seem complex, but the core idea is intuitive once we break it down. So we have in the diagram always the sender sequence number. And we know that the green blocks is the last bytes that were acknowledged, or the last data that was sent, and we received an acknowledgement for them. We have our yellow bytes. There are segments that are called in-flight, They have been sent, but they have not been yet acknowledged. So these are the in-flight network. The blue here represents the sequence number that could be sent next. This is the space TCP uses without exceeding the congestion window limit. And then anything beyond that, like the gray area we have here, is it can't be sent yet because doing so would mean TCP is sending too fast and it would cause congestion for the network. So how do we make sure that we are staying in the window size limit and we are not causing congestion? So TCP uses the limit transmission where that the last byte that is sent, and that is the green byte, or the last byte that was sent, which is the yellow, minus the last byte that is acknowledged, which is in green, less than or equal to the congestion window size that we have here. So the sending behavior on the right that we see here is that we send up to the congestion window size in bytes, and we wait one round time trip for acknowledgements. Then we send more bytes as more acknowledgements come, but the sending rate must have a specific limit or a constraintive way that we don't make congestion. So it's kind of roughly that we have the congestion window size over the round time trip that shows a direct link between the congestion window size and throughput. So, and then we know that TCP, the window size or the congestion window updates dynamically. Once we receive more acknowledgements, we can pass or move on to the next +1 increment of the next data to be sent. Does that make sense so far? Is everything clear? Okay. Okay, so we've seen how TCP manages its congestion window size during steady transmission, and that is using the AIMD. Now, we want to see what happens when we start a new TCP connection that begins. So this is the phase that is called a slow start. And despite the name that you see here as a slow start, it actually increases very exponentially or very quickly. That is very fast. So let's see how that takes place. First, at the beginning, we send the first segment, and that is one round time trip. So once we receive the acknowledgement, we can go ahead and send two segments. So for every segment that comes back, we double it and then we send it back. So here in the example we send two segments. After that, we send 4, then 8, and so on. So this doubling continues, and that is why we have an increase or exponential increase of sending. It's not actually slow start, but we must reach a limit when we see the congestion phase. So even though this is called slow start, we know that it actually grows exponentially and it ramps up to incredibly fast. So how it works is basically TCP begins being cautious, it learns quickly, and then it accelerates until congestion appears. So, and that goes back to the AMID algorithm that we discussed in the first few slides. That is just showing you how the starting phase happens. So we saw how in the slow phase, how slow start ramps up very quickly. The next question is, we want to know, when should TCP stop increasing exponentially and switch to a more cautious linear increase? This is basically the same analogy. When can we know, hey, to stop decreasing when driving is basically if we have traffic or we see brakes or we see an accident, we start to slow down. How do we make sure that we are decreasing in this specific aspect? So the answer lies in a threshold called SS thresh, and this is the acronym for slow start threshold. So when the congestion window side goes about half its previous values before a timeout, TCP assumes it's getting into a congestion. So from that point, TCP starts growing exponentially rather than linearly. It switches, sorry, from exponential to linear growth. And I'm gonna explain here in a minute. So the graph itself, when it reaches the SS threshold, the slow start threshold, it switches from doubling and growing exponentially to linearly. So the diagram here that we have compares the two variations of multiplicative aimed algorithm that we spoke about, TCP Reno and Tahoe. We know Reno cuts the window size in half, and we know TCP goes back into one. So here it's under the assumption that we have multiple segments on the y-axis that are getting sent. So once we reach the 16 mark, we take the SSS threshold, and that is basically kind of the indicator for us to start slowing down. And from that point, it starts sending linearly, not exponentially. So it goes from 8, 9, 10, 11, rather than 8, and then it doubles always to 10. Here we have an increment of 2. And then once we reach that congestion phase, we go back to our two approaches, the TCP Tahoe and the TCP Reno, and depending on which one that we use, it either gets cut in half. So here the X mark is at 12. So when we use TCP Reno, it drops to 6, then we start going linearly from there. So 7, 8, 9, 10, and up until we reach 12. That is the congestion indicator. TCP Tahoe goes all the way down to 1, starts from 1 again, and then it makes its way up. But the way it makes its way up, it doesn't make its way up linearly, it goes exponentially. So that is the idea. So in summary, this specific mechanisms lets TCP avoid congestion gracefully instead of crashing into keeping the throughput high but stable. So that is the main idea that we have. Here we're gonna do kind of like a summary of TCP congestion control with the FSM or finite state machines. We want to show how the TCP moves between different phases based on what's happening on the network. So it's basically like a TCP control loop. So it reacts, it adjusts, and recovers on its own. So the first phase or the first finite state we have is everything begins in the slow start. So the sender starts with a small congestion window, which is 1, and that is the maximum size. We start with 1 because we're probing or casually testing the network to see that feedback. From the given feedback, we can go ahead and adjust. So for every acknowledgement that comes, we know that we increase the window size, so we double the runtime trip. So when we wrap up very fast, so we know that we leave the slow phase into an exponential or a very quick phase by exponentially jumping. But we know that this can't go forever because we'll reach a phase where there's a bottleneck or a congestion phase. So once the window size, the congestion window size is bigger or equal to the slow start threshold, then we go into another state, which is congestion avoidance. And then we start cutting down, and then we go linearly. So in the congestion avoidance, what TCP will do is that it probes to find available bandwidth carefully. So adds about 1 MSS per round time trip to avoid pushing the network too far. If the sender starts receiving duplicates acknowledgement, this is a sign that a packet was lost, but other ones are still getting through. So it's still kind of the same idea of TCP for reliable data is also involved in congestion control. And then when after the initial the second phase that we go through, which is a congestion avoidance, we go to a fast recovery phase where TCP enters fast recovery. So instead of resetting everything, it slightly reduces its congestion window size and keeps sending data to stay protected. And that's what we use for TCP Reno. We don't cut down and go all the way to 1. We cut down based on the slow start threshold that we have. And then here, if we have a timeout that can occur, because we have the timeout is another indicator that we are using to know that data has been congested or lost. There meaning there is, that's a stronger sign of congestion as well. So then the TCP cuts its window size back into 1, and it goes back to the phase of slow start. So this is getting repeated. So it's kind of like a back and forth behavior for us. We start going fast, we slow down, and we recover. That allows TCB to kind of stay adaptive and responsive. So in summary, or a brief recap is that we slow start, um, and then we grow fast, leaving the slow start phase. Then we reach congestion avoidance, then we fine tune our speed. Then we have a fast retransmit or a fast recovery that handles the losses that had happened. And this what makes TCP more stable, fair, and self-correcting across the internet. And obviously the timeouts or the acknowledgements are the indicators that are helping us with this. If it's a positive acknowledgement, that means we can increase the window size. If it's a negative, that means we must fine tune. The timer is kind of the same thing. If the timer runs out, then there's something that's going on, and we have to fine tune until we get back to the regular phase where we receive positive acknowledgements, then we can increase the segment size. So now we move to TCP cubic. This is also another algorithm. So over the years, they have developed newer algorithms or modern congestion control algorithms, and they are used widely. So TCP cubic is actually very familiar or very famous in Linux. So it builds on the AMID, the additive increase or the multiplicative decrease. But here we are asking an important question. And the question is that we are asking, is there a better way than AMID to probe for usable bandwidth? So how do we probe for bandwidth than just linearly increasing for the window? So the key idea we have here is that it comes from observing the W max. This is the congestion window size where a loss was last detected. So once we have a loss, we mark that as the W max. This is the last time that a loss was detected. And the W max is going to be an indicator for us to say, hey, this is the highest sending rate the connection has achieved. So the TCP cubic, what it does is that assumes that the network capacity hasn't changed drastically since the last congestion event. So rather than having that recovery or the increment bilinearly, we grow very fast. And I'll show you how that happens. So instead of increasing linearly, we said cubic growth function is based on the elapsed time since that last loss. So after cutting the window in half, like the traditional TCP using Rhino, it ramps up quickly fast. So then it slow starts near the WMAX to avoid overshooting again. So this is what happens. So we know WMAX is the highest sending rate for us. Once we receive that, we decrease, we cut in size. So that is using the TCP Rhino. But here, what we are doing is that the classic TCP would grow linearly. TCP cubic grows very exponentially, very fast, but it keeps in mind the WMAX. So it doesn't overshoot over the WMAX because we know the WMAX is the highest sending rate of a phase that is given. So we can do a faster retransmit, a faster recovery in the essence. So that would happen again, the recovery process for us. And what that does is that this will result in a higher throughput and better performance on modern high bandwidth and high delay. So it spends less time utilizing again to find the optimal sending rate and adapts more smoothly. So it's kind of like leaving a remark for us to know, hey, this is the best phase for us to send at. We can go there, grow very fast, but we have to keep in mind so we don't overshoot. So cubic, TCP cubic, kind of keeps the same fairness as AIMD, but probes bandwidth more intelligently and efficiently. So we want to see how this exactly works exactly. So the key idea is that, we have an introduction of a new variable here. It's the K, and the K represents the point in time when TCP expects to reach WMAX, and The window size is where the last congestion has occurred. So the first thing that we do is that TCP cubic picks a future time k, and this is when it wants the window size to go back up to W max. So we are not blindly increasing, we are planning ahead. We are marking the W max as a phase for us, and that is kind of the planning that we have here. And the value of k can be tuned here, allowing flexibility based on the network characteristics. And here the cubic increase is congestion window size as a function of the cube of the time difference between the current time and k. So the rate of increase depends on how far away we are in time from the target point. So this kind of has an interesting side. So when the sender is far away from the k, the increase is larger. So TCP grows very aggressively. But when it's close to the k, it says, hey, we start to slow down. So that's the difference between TCP cubic and Reno. We know that TCP Reno, once it reaches that congestion phase, it grows linearly. We know the cubic grows very fast, but has an idea or a number of the W max, so it doesn't overshoot. So because of this TCP cubic or the efficient or mechanisms that are given to us, it became like the default algorithm or default congestion control algorithm. And it's, I said, mostly wide used in Linux, and it's now being implemented in major web servers over the internet. So it provides better throughput than AIMD, and high speeds, long distance links. So it maintains also fairness and stability across. So another analogy for the TCP cubic to get you an understanding of that. So far we discussed TCP AIMD, and this is TCP cubic. So we're sticking with the driving on the highway analogy, but now imagine you're an inexperienced driver with a smart cruise control system. So like you set it to a specific speed. So the step one is to remember the last safe speed. So the last time you hit traffic, you note the maximum safe speed before the congestion happened. So for example, say it was 65 miles per hour. So you don't want to instantly go back there, but you also don't want to crawl forever, like increasing from 1, 2 to 65. You want to shoot very back quick to 65, but also remember that overshooting point, which is the mark, the W max. So this is like the cubic remembering the previous congestion window. So this is the last point before a packet loss occurred. And the curve shape that we have, which is linear with TCP Reno, but with cubic is exponential growing. So after you slow down, you begin to gently accelerate. So at first slowly and then faster as you get farther away from that congestion point. So your speed increases following a smooth curved pattern, not a straight line. And that is the cubic function that we have. Part that the window grows as a cubic curve with time since the last loss. And then step 3 is you're going to be careful near the limit, careful near the W max. So as you approach that 65 miles per hour mark, you slow the acceleration again. And maybe you go down to 60, 63, whatever it is, testing the road carefully. And then if there's no congestion that happens, you push beyond that and go a little bit faster. So this is like the cubic region near W max. So it grows slowly down near the old limit, then accelerates past the network seems safe. Okay, so now we go back to the general overview, and this is the figure that we have for congestion, for data sending, packet loss, packet congestion. So this is our initial figure that we had. So we want to analyze the bigger picture. So we know that both classic TCP and cubic TCP, they increase their sending rate continuously. We know that. So as long as we are getting packets acknowledgement. But eventually what happens is that this growth has a limit. So somewhere along the path. So maybe one router becomes very saturated, and this is called the bottleneck. So it is the slowest route or part of the network. And here in the figure that we have a source and a destination. And obviously we're in the transport layer, which is the second layer after the application. And we have multiple routers, multiple paths that are getting through. And the bottleneck is going to be the route or the path that is heavily congested. So we want to know how we can deal with that. So it's almost always busy. After the bottleneck happens or the congestion happens is that the packet queue is almost full and sometimes overflow. So the buffer causes overflow and it causes packet loss. So this is the congestion link where TCP detects the loss and reacts by slowing down. And remember, in most real networks, it's not just your flow that you are working with. There are other multiple TCP flows that are all competing in the same bottleneck bandwidth. So how do we make sure fairness is applied to all users? And how do we make sure that congestion doesn't happen for all users? So now that we know where the congestion happened on the given paths, we can neglect the other paths. We want to focus exactly on the bottleneck link. That's where the TCP behavior really matters. So we'll ignore the other routers since they're not in the problem. So what we do here is that a couple of insights that I want to give you is that when we have the bottleneck of the given path, an important insight is that if we increase the TCP sending rate, it does not really improve the end-to-end throughput anymore because the router can only push packets at its fixed output rates. So no matter how much faster the sender tries to go, there's also going to be a bottleneck that is, or a congestion that is happening. So there's really no use of increasing the sending rates. The second observation is that as the sender increases its rate, you'll notice that our runtime trip goes up because the packets start queuing at the bottleneck. Once we have a congestion phase or packets are getting lost, obviously the runtime trip goes very high for this given segment or this given packet. And the last thing that we have is that the goal that we are trying to do here is that it's not just to push endlessly, but it's to keep the end-to-end pipe full, but not fuller. So we want to send packets depending on the specific path that we have, but we don't want to oversend where it causes congestion. So that is the balance where TCP congestion algorithms work or take place. Like we discussed, the AIMD or the cubic there, and they're designed to maintain so this problem doesn't happen. So now we shift to another approach. This is kind of like called delay-based approach. So you can consider this as another algorithms. So the main idea here is that we want to make the network pipe that is the bottleneck just to be full, but not very fuller. So we want to keep the bottleneck busy sending packets, but we don't want to overwhelm it where delay happens. And once delay happens, buffer starts to flow and then packets are getting dropped. So with the delay base, what we do is that the sender, what they do is they measure the runtime trip for its packets. And then from these given measurements, it identifies the runtime trip minimum. This is the smallest runtime trip that is observed so far in the testing phase. And that represents the uncongested path with no queuing delay. And then using that, the sender can compute the measured throughputs. So the number of bytes sent in one runtime time interval divided by the runtime trip value. So it can compute or it can compare this uncongested throughput, which would be like the window size, the congestion window size over the minimum runtime trip. And then basically we're going to have kind of like a classification or an indication is that if the measured throughput is very close to the uncongested throughput, that means the path isn't congested. So the sender can say, hey, we can increase the window size or we can send at a little bit of a faster phase or rates. But if the measured throughput is much lower, it means the path is congested. So what we do is that we start decreasing. So that is the basic idea of delay-based congestion. It relies on measuring the delay instead of packet loss. So it controls how fast TCP sends. So basically, if we think about it, TCP, and when it comes to the delay-based congestion control, it focuses on avoiding congestion before it happens. So we don't want congestion to happen, then we react by decreasing, then increasing after we go to the regular phase. We want to avoid the congestion before it happens. Or the goal is to keep the bottleneck router busy, but not overwhelmed. So in other words, keep the pipe full or just full enough, but not full. So a modern, to tell you like a little bit about a real world or switch a little bit, is a modern example of that is the BBR, is the bottleneck bandwidth round time trip propagation time that was developed by Google in 2016. So it estimates the bottleneck capacity and the minimum round time trip, then adjust the sending rate accordingly instead of waiting for losses. So that is a way, a safe way for us to measure congestion before it actually happens. And now it's like widely used across Google internal backbone and also used by YouTube and other Google services. And they kind of replaced the older algorithms like Cubic or AIMD. So this is the delay-based TCP analogy of that, and this is going to be like the last, I think, the analogy that we have. So unlike AIMD, which reacts to crashes, or Cubic that remembers the last congestion point, delay-based tries to sense trouble before it actually happens. So step one, you're actually just watching the road, not just the speed. So you're driving on the highway, but instead of waiting to see traffic jam or slamming the brakes, you watch the brake lights far ahead and you feel the small slowdowns in traffic flow. That's like monitoring the round time trip. So when packets take slightly longer to return, it is an early hint for us to say that there is a queue that's going to be building up. So then we go to the second phase, second step, where we adjust smoothly. So when you notice those brake lights or small delays, you ease off on the gas pedal just a little, keeping a safe distance before a jam actually forms. So now this is where the sender reduces its sending rate when the delay is measured. So it avoids packet loss. And that avoids overworking the network with packet retransmission, because we said when we retransmit the packets, yes, we are making sure that data is getting resent, but that is also bandwidth that is getting used over the network. So accelerating when it's clear. So if the traffic smooths out and the road opens, you press the gas to regain the speed. So when the delay goes back down, the sender starts to increase its window size again to use the available bandwidth. So now we finished the first approach that we talked about in the last lecture, that is end-to-end. We talked about TCP, congestion control when it comes to AIMD. We talked about TCP with Cubic, and we talked about delay base. So these are all end-to-end approaches. We have not used or configured or added the network assisted congestion control. So this is where we move to the ECN. And this is the second approach where the network itself is involved. And one of the most known algorithms is the ECN. This is a way to avoid packet loss while still indicating congestion before it comes critical. And we'll see how this works. So how ECN works is it uses 2 bits in the IP header that is found in the type of service in the field, because we have for each segment or for each packet that is getting sent is going to be a field. So the type of service is the field that we use for these 2 bits. So the routers can mark those when they detect congestion. So the policy for when to mark these bits is usually set by the network operator. So that is configured from one network admin to another. So let's see how this works. So if instead of dropping the packets, what we do is that congested router will mark the ECN and bits that are passing through, as shown in the figure here. So this tells the downstream nodes that the path is getting congested. So we have an ECN of 10 because we use 2 bits for that. So what would happen after is that when there's congestion, when the destination receives this ECN, okay, so yeah, when the destination receives the ECN marked packets, it sets kind of like an ESN echo, and that kind of is like a flag. So it sends it back to the sender. So if it kind of messes with the bits. So the bits that we send in the original, what we have is 10. once we go through that congestion or bottleneck path, those two bits get changed. And basically, it's an indicator that that there's congestion, so it goes to 11. And then once it goes to the sender. When it goes to the destination sends the acknowledgement back to the sender or the source. It also gives them kind of like an insight of what happened. So it's telling you, hey, there was congestion in this specific packet. I need you to slow down the sending rate for the next given packets so that we don't avoid this again. So we use here the network as a part of to assist in network or data congestion. So overall, the ECN, the algorithm, which is a network-based approach, it combines the IP layer marketing, uses the ECM bits and TCP layer signaling to give that indicator. Does that make sense? The second approach? Okay. Go ahead. Yep. So that's so now we kind of finished with the approaches or the algorithms for congestion control or TCP congestion control. So now we're moving to TCP fairness. So we want to talk about fairness, where we ask ourselves the question, hey, when we have multiple TCP flows that share the same bottleneck, how eventually do they share that capacity? So we have two TCP connections here, and TCP is utilizing more than TCP connection 2. So how do we make sure there's a fairness state between both of them? And the fairness goal here that we have is very simple. So if there are k TCP connections sharing the bottleneck of total bandwidth R, then ideally each should get R over k bits per second on average. Yeah, so in theory here that we have, each TCP connection, either one or two, should get half of the available bandwidth. So it's behaved fairly. So it's kind of like analogy of there's two people eating pizzas, and we have 8 slices, so it would get split in half. But how do we make sure that happens? So that leads to another broader question: does the algorithms or TCP versions that we discussed so far, like Reno or Cubic, actually achieve this in fairness practice? So we want to take a look at that. So a really nice way or intuitive way to understand TCP fairness is by using a two-dimensional flow plot. So it shows the throughput of two competing TCP connections sharing the same bottleneck. The diagonal 45 line represents the perfect fairness. So both flaws are getting equal bandwidths. That's what we said. It has to be equal with both. So let us say that the connection is the starting red dot. So obviously we have a start phase, and that is the red dot. So here the connection has higher throughput than connection 2, obviously. And we need to make sure their combined rate is below the total link capacity. So then the flow for this would start increasing, and then we use the different algorithms to whether it's cubic or AIMD, and there's going to be a lot of like up and down, you can say. So there is we start speeding up, and then we use the algorithms to reduce the congestion, and it keeps happening again, and basically the cycle repeats up and down, diagonally back and forth. So over these different cycle that we had with up and down, we want to make sure that it is both users or both connections are getting an equal bandwidth share. And we saw that with the red line, it starts with the initial connection, but it does not go and overuse the bandwidth that is shared or given to connection 1. So is TCP fair, or does the algorithms that we discussed ensure that there's fairness? So yeah, under idealized assumptions, we have the same runtime trip, we have the same number of sessions, and both congestion avoidance. So yes, TCP is fair. So as we see here, does that make sense as well? Any clarification that's needed on that one? Okay. So we discussed fairness for TCP, but we want to take it to a bigger perspective because not all networks actually use TCP. We said that multimedia applications use UDP instead. So they prefer to send at a constant rate and they can tolerate some loss instead of being slowed down by the congestion control. So here with UDP, flow can end up being unfairly competing with TCP flows in the same link. And obviously, there is no internet policies or internet police that says and that enforces fairness. So apps can do whatever the developer allows them. So even TCP can bend rules a little bit. Some open, some actually open multi-parallel connections to boost speed. So web browsers are a good example. Um, and the idea is that, and I have a deeper example with that. So if one app uses one TCP, it gets R over the 10 of the rate. But if it opens 11, it can get almost as R over 2. So practically or in practice, when we switch to practice, not algorithm based, fairness isn't really enforced because we don't have no way of enforcement. But the TCP congestion control still keeps the internet, and thank to that, the TCP congestion control that we have or the algorithms is what keeps the internet stable and usable. So that is a wrap of TCP congestion control. Does anyone have any questions? Okay, so we have about 20 minutes. So we're going to talk about the evolution of the transport layer functionality. So over the past 40 years, it's kind of a little bit of history. TCP and UDP have been the core transport protocols of the internet. So when you think of the transport layer, the two known are TCP and UDP. So everything from web browsing to emailing or streaming apps on the app uses these two. But over time, we have seen different kind of like variations or different flavors of TCP that has been developed for specific network scenarios. And they there's new ones that are getting developed for certain case scenarios or for certain network infrastructures. So for example, if we have long fat pipes like large data transfers, um, the challenges that we face with that is high capacity links. A single packet loss can stall massive transfers. On wireless networks, packet loss is often caused by interference, not congestion, but TCP can't tell the difference. Also, we have a scenario of long delay links, so like satellites that face very high runtime trips. Also, data center networks where it needs extremely low latency, and background traffic flows um, are designed to stay low priority to avoid interference with critical traffic. So now moving a little bit forward, we said that those are the traditional transport layer protocols that we have. Most recently, now we're talking in modern, moving up to the some of these transports functions that have been moving up to the application layer. So like HTTP3, and a key example of that is QUIC or Quick, which builds transport features like reliability and congestion control on top of UDP for better performance and flexibility. And we'll see how this works. So Quick or QUIC stands for Quick UDP Internet Connection. It's like an application layer protocol that is built on top of UDP. So traditionally, the traditional way that we had is that we know HTTP runs on top of TCP and can also use TLS for security, right? And this adds another state and another handshake of kind of delay because we are trying to make sure that data is being sent in a reliable way. So Quick came and said, no, we're not doing that. It changes by moving the transport features into the application layer. So because we said Quick is a built up on UDP, so we still have our IP, we have UDP, but Quick has moved and said, hey, I'll combine kind of do a combination of both. So what we have here is that quick change that movement. So move by moving transport features into the application layer. So that is the idea here. And it also integrates TLS encryption and supports multiplex streams without adding blocking. So that is the design that is kind of the foundation of HTTP3, which delivers faster and more connections efficient for modern internet. So quick builds on the same ideas that we have seen in TCP. And we've seen things in TCP like connection setup, error control, and congestion control. But it's kind of like reimagined for speed and flexibility at the application layer. So the first thing that we have is that error and congestion control. So quick design intentionally mirrors TCP logic. That we said that. And also connection establishment. So we said quick QIC combines reliability, congestion, control, authentication, encryption, all in one single state. So it reduces the handshake process or the initial process. So that means it can establish a secure encrypted connection in just one round time trip. So it is much faster than TCP or TLS handshakes. And for streams, when one QIC connection can have multiple independent streams of data. So each stream itself has a separate, reliable, and security, but they share common congestion control process. So let's see how this works. We have on our left-hand side, the TCP, and this is the traditional TCP connection. So on the left, we have, we will first perform a TCP transport layer handshake. This is to make sure that both server and client are intact. Then we do TLS handshake to handle authentication and encryption. These happen actually one after another. So data can be exchanged until both of these are completed. Then QIC handshake would do combines, as we said, into a single handshake. So it just sets up reliability, congestion control, encryption all at once. So that reduces the setup time with just one round time trip. So this is the design that is why HTTP3 can start transferring data faster than traditional TCP-based approaches. So here we want to compare TCP requests, how they are handled over traditional TCP versus QIAC. So on the left-hand side, first we're going to talk about HTTP 1. So HTTP 1 actually, when we want to see where multiple requests are sent across the TCP connection. Okay, so what happens is that we have a HTTP GET. After we do the handshake, there we have an error, so we stop. We make sure that is getting taken care of. Then it gets sent over. Then we send that last HTTP GET. So something to look at. Maybe I can stop this. Okay, so the first thing to look at is the A side of the slide. We have the application. We said the application uses TCP as a protocol, but also has its TLS. The initial process is going to be very longer compared to QIC. For the transport, we use TCP, and RDT is reliable data transferring. And we also have TCP congestion control, so it provides that for us. And the models that or the algorithms that we have studied in the past slides is exactly being implemented on the left, where we don't skip over. So UDP on the right-hand side, what it does is that basically takes congestion control and reliable data transfer from TCP, combines it also with encryption. So we'll see how that works. So there's parallelism here and there's no HOL block. So we have the second GET and there's an error. We can go ahead and proceed to a way of parallelism. We can take care of the third one. And the idea is used here in HTTP. We're not using it really in networking or data transfer because we know that packets needs to be sent in order. But with TCP, when it comes to HTTP, when you're opening multiple links or multiple web pages, it doesn't really matter to you if this opens first rather than the other ones. So you can open multiple pages and this one could load quicker or faster than the other one. So on the right, QX solves by creating independent streams with a single connection, and each handles its own retransmission. So one lost packet does not stall the others, like we see in the traditional TLS and TCP. So this allows true parallelism, faster page load, and smoother app performance. And that is it. So that is it by chapter 3. So we discussed the principles behind transport layer service. What does the when we look at the whole OSI model, and when it comes to the networking infrastructure, we know what the application is used for. We have studied that. We know what the transport layer does. What is included in the transport layer is multiplexing and demultiplexing. We talked about RDT. How can we achieve reliable data transfer? We talked about flow control, how we can make sure that the receiver is not overwhelmed with data. And we said that we have a sequence size that is being set by the receiver saying, hey, don't send me more than this specific size. Congestion control that we talked about, we said there is end-to-end approach where the network itself is not being used. And the algorithms in the end-to-end approach, we have AIMD, we have TCP cubic, we have delay-based, and the second approach that we discussed is the ECN, I think, for where the network itself is involved. And the bits is an indicator for us that, hey, the packet went through congestion. It's telling the sender to slow down your rate. So installation, implementation on the internet, we talked about UDP and TCP, and we talked about the newest or modern improvement, which is QIC, and it's highly used in HTTP. So what we have up next is going to be, we're going to leave the network edge. So we're going to leave applications and transport layers. Doesn't mean we won't talk about them in scenarios or examples over the next lectures, but in the network core, we're going to dive into the network core. So the next chapter is going to cover a network layer, and we are making our way down. So we're going to cover the data plane or control plane, and we see how that works with. Have you guys heard of SDN, software defined networking? Yeah, so that is something that we're going to study as well. So it's like basically a controller hub that makes sure that all devices or applications has one single kind of use or that makes decisions for the whole network. So yeah, that is it. That's what we have. On Zoom, if you don't have any questions, you are free to go. Also, you guys in class, if you don't have any questions, I will see you on next Wednesday, because Wednesday we won't have class. I'm gonna release an announcement sometime on Wednesday to make sure it's an official announcement and make sure that everything is clear. Monday is the midterm. I wish you guys good luck on that. And then I'll see you next Wednesday. We'll talk about the transport layer. Yeah, you as well. Thank you. Thank you.